Hi, my name is Nolan Rudolph, and I will be presenting new capabilities for self-driving networks. Now, to provide a little background on what exactly a self-driving network is, simply, it's a network that runs entirely by itself. It does this by utilizing automation. Everything is completely automated. It is dependent on real-time telemetry and analytics, and it will use this information in real time to make decisions on its own accord. And in the instance of an attack or some risk, then it should have the ability to self-remediate. Now, how is this innovative? Well, self-driving networks or self-DNs exhibit a lot of differences from today's networking services in a positive manner. For example, there is no scrutinization required by some network administrator. It should be able to run by itself. Um, the machine learning techniques it utilizes should increase its efficiency and tolerance, so the throughput will increase, and it should also be able to combat attacks much better. And lastly, uh, but many more points, it reduces network complexity, and there's this notion of unified networking. Now, the research objective is to create new capabilities for self-driving networks because in today's world, we lack self-driving network compatible software since the networks are a little bit out of date and everything is created for them. And I intended on making three particular capabilities: a visualization framework, NetFlow to packet synthesizer, and a driver space flow collector. So we'll begin with number one. Now, the requirements of this is that it will be flow level based. So it will only contain flow level data. Now, flow level data is what type of packet is it? Is it UDP? Is it how long was it coming for? What was the size? It should have real-time depictions of network traffic, and it should be scalable in the instance of heavy amounts of traffic where there's just a lot of congestion. You should be able to visualize that. And lastly, it needs to be influenceable by an administrator. Now, there's a lot of trials and tribulations that went into finding the proper software that would help me achieve this goal. Some of them were Gephi, Excel, and Tableau. And the reasons why they didn't work were a long computation time. There's no real-time applicability. Storage was an issue. And so finally we come across Grafana. And Grafana was great because Grafana uses a MySQL database to create its visuals. And this allows us to implement real time, right? Because we can constantly update this MySQL database and add this notion of real time. And it's also great for storing flow level data, which we can see by the table, the top right image. It can store all types of data, and it's perfect for flow level attributes. Now, there are millions of flows that can be depicted in seconds. I've tested it many times, so it obviously has great scalability. And lastly, we can customize what types of flows we want to see, and this is the influenceable assets part that was required of our software. And we can see this in the bottom right image. We can select different parameters, and we can choose what packets we wish to see. And here's a simple graph. We can see in the bottom left, there's the different protocols that is entailed by this graph, and we can see some spikes. So that would be interesting to check out. And we can see we can get even more information by selecting a region. So that accomplishes the visualization framework, and we'll now turn our attention to NetFlow to packet synthesizer. Just as the last one, we need scalability and real time as two of the objectives. And now for the scalability, it needs to replicate heavy traffic, and for the real time, it will synthesize real time events. Now, it needs to be accurate. This is new. It needs to almost perfectly replicate traffic. It needs to be an accurate synthesizer. And now the arguments it should take on is a set of NetFlow records, an interface to deploy these packets on, and Ethernet endpoints, which will include where the packet is going to. Now, the functionality should replay the data as it was recorded, and it should be able to send to any actually accessible endpoint out there. And this slide is how I implemented it. Now, I wanted to add this real-time element and I did this by only reading in data that was applicable to a current time frame. So if we start at our software at 0 seconds, we should only consider the flows that came in the first 10 seconds, not reading it all in at once. That would also be terrible storage. Round robin network scheduler was implemented, and this is known for its scalability because it gives all flows equal time. If one needs more time, it'll just rapidly send that guy, and it'll come back around to it. We use the C programming language because it has low-level interaction with the system, which furthers the throughput and scalability. We use the NetInet repository because it has collections of headers, which are entailed by the packets used to transfer data. And lastly, we use sockets to actually initiate the request and send over links. Now here's some results. We have a packets per second. We see that it starts to tinker off around the 1 million packets per second point. I made sure to stress test my system and see when exactly it started losing the efficiency, the accuracy. On the right, we see the bits per second, which these kind of go hand in hand. Now, I'll readjust my guy here. I wanted to compare this to the state-of-the-art packets per second. I think packets per second is the most important objective. And this only considers kernel space packet generators, which is where mine operated in. Now on the left, we see my software, which I apologize for the flipped axis, but we can see mine is around 0.8 million packets per second. And the state of the art, which is TCP replay for kernel space, is around 0.95. So this shows that my software competes fairly well. Okay, let's go ahead and readjust this guy. We now turn our attention to the driver space flow collector. What's a flow collector? A flow collector listens on some interface for packets coming in, and it will be able to decipher these, de-encrypt these packets and gather these important flow level attributes of each of these packets. Why driver space? This is very intimate with this machine. It is very low level. It allows us to directly communicate with the machine. This kind of goes hand in hand with kernel space, but we'll see in a later figure, it's not exactly kernel space. This is accomplished using two acronyms that I'll describe, which is EBPF and XDP. Now, the EBPF stands for Extended Berkeley Packet Filter. This is ran from the user space, and it attaches something onto a kernel. This something is the express data path. And what the express data path does is it can actually communicate with the packet. It can dissect the packet before it even reaches the inner system. So there's no socket buffer that is required, and it is extremely efficient. And lastly, eBPF offers dynamic replacement of programs, which is an extension off of the original Berkeley packet filter. And on the right, we can see the throughput of XDP in comparison to well-known other layers, such as the socket layer, for example. There's really good throughput. Now, eBPF segregates modules into two categories, user space and kernel space. In user space, I have a Python script, and this tells the computer where to mount this hook, what type of program I'll be using, XDP, and it retrieves information from XDP. In kernel space, which is implemented in C, we actually have the XDP program, and this operates within the packet space. In fact, if you go outside the packet space, it starts to complain. And this is extremely efficient. This just brings home 1,000 times over how incredibly efficient this is, because it is directly interacting with what is coming to your computer before it even reaches the machine. The data exchange that is used between these two spaces is a system of maps, which are key value stores. And as I said, it allows interactions. And so far, here are the results. You mount them onto you mount the XDP onto some interface, and we can see that it picks up these different flows. I was constantly ransacking my computer with requests from a remote server, and this is what we were able to observe. And it also outputs the information to a file, so you can look over it at a later point in time. In conclusion, this set of capabilities creates a very reliable system for retrieval, visualization, manipulation, and dispersion. These are all very crucial for self-driving networks. I will also continue working on the driver space flow collector, and in doing so, this essentially entails looking at different packet attributes like how long has the connection been held for, and I also want to implement a system of aggregation where it drops the flow after a set amount of time without any further pings. And lastly, implementing per CPU mechanism. This is just known to increase throughput because you can use multiple CPUs to run your program, which will speed up everything about it. All right. And that's about it. Thank you so much for watching, and I hope you'll enjoy.